Hello everybody, in this lecture we will be solving 1998 IMO problem number 6. Here is a view of this problem. Consider all functions f from the set of all positive integers into itself, satisfying the following functional equation for all s and t in the set of positive integers. Determine the least possible value for f of 1998. So let's start by assigning f of 1 the value a. So therefore, if we first start by setting, with this assumption, if we start by setting t is equal to 1 in our functional equation, we would get f of s is equal to s f of 1 squared, but we just established that f of 1 is equal to a, so therefore we have s times a squared. In a similar way, if we plug in s equals 1 in our functional equation, we would get f of t squared, f of 1 times f of 1 is simply equal to 1 times f of t squared, which simply implies that because f of 1 is a, we would get f of a times t squared is simply equal to f of t squared. Now, if we take any two positive integers, and if we set in this equation here, in this equation, if we set, let's start with this, and then if we set s is equal to ay squared, that would give us f of ay squared is equal to ay squared times and a squared, or you can simply call it a cubed times y squared. Now we go back to the functional equation again, and this time we plug in t is equal to x and s is equal to f of ay squared. So far this been 1, 2, 3, I think. And then this is the fourth trial. This is a standard functional equation problem where you've got to plug in lots of stuff. Okay, so when we replace t with x, we would get f of x squared times f of s, but s here is this expression, so f of a times y squared. I think I need to close the third time, and that's simply equal to s times f of t squared, s times, so s is this, times f of t squared, so that's just x squared. Oh, sorry, f of x squared, sorry for that, times f of x squared. Now we just have discovered in 3 that this thing is simply equal to a cubed times y squared by 3, and in a similar way we have also discovered, yes, here this one is equal to f of y squared by 2. So therefore this expression that we've got here reduces to f of x squared times a cubed times y squared, that's an a, is equal to f of y squared times f of x squared. Now in this equation here, in equation 2, then in the result for 2, if we plug in t is equal to axy, we would get so plug in t is equal to a times x times y, we would get f of a times axy squared, right, is equal to f of t squared. So this thing is equal to f of t squared, which is axy squared. And well, notice that the left hand side is simply equal to f of a cubed times x squared times y squared, and this is precisely the left side of equation 4. So and this thing is apparently equal to this, so therefore 4 and 5 combined would give us, so the left hand side is just this expression here, a times x times y squared, and this is simply equal to f of x squared times f of y squared. We can take the square root of both sides, and knowing that the values of f are only positive integers, so that would give us f of a times x times y is equal to f of x times f of y. Recall that a is simply the value f of 1, and this is true for all x, y in the set of positive integers. If in this equation, so this is what we got so far, if in this equation, if we further plug in y equals 1, so you can call it 6 if you will, we would get that f of ax is simply equal to f of x times f of 1, but then this is just equal to a f of x. But in view of what we've got here, this would simply imply that f of axy, the left hand side, is basically equal to applying this formula. You can think of this as one term, a times f of x times y, but that thing is apparently equal to f of x times f of y. So this would imply inductively, for instance, let me actually show the induction. So let's for instance start with this expression here, x to the power k. You multiply them, that's simply equal to, by a simple trick, you can split the a as such, and in a similar way you can split inside as such. And now notice that this expression here, if you consider this as the y, like in this one, would simply be equal to a, we have this term remain, and then a times f of this thing is just equal to, you just split it, f of x times f of x to the power k minus 1. And you can continue this procedure. Let me do it one more time. So a to the power k minus 3 times a, right? And then we have f of x times f of x to the power, okay, so let's split this one as well, x k minus 2. Now this is simply equal to, if you focus your attention on this expression here, but that's just this guy again. So we have a to the power k minus 3 times f of x times, we can split this as f of x times f of x to the power k minus 2, which is simply equal to a to the power k minus 3 f of x squared f of x to the power k minus 2. So if you proceed in this fashion, or if you say, if you would like, you can prove it also by induction, that our function here, for instance f of x, here it had a power, or let's focus on this one. Compare these two expressions here, this one with this one. We just realized that the power of f of x here was 1, and as you added these two terms, their exponents, so it would be k minus 2 plus 1 is k minus 1, the same thing here, k minus 1 here. So therefore, and by the way, adding these two would get k fixed. We can continue this procedure until we reach that this guy basically becomes f of x raised to the kth power. All the a's as a result vanishes, and all we got is a power of the function f of x for k equals 1, 2, 3, and so on, for all positive integer values of k. So at this stage, I would like to make the following claim, that all values of f are integers divisible by a. So therefore let's say a divides f of x for x in n. So to prove this claim, so we can prove it. We can fix this x in n, and then consider a prime. So take p, which is a prime. Oops. Okay. So we take this prime p, and let's assume that let p to the alpha be the highest power of p dividing a. So therefore p to the alpha perfectly divides a, and similarly, and let p to the beta perfectly divides beta be the highest power that of p that divides f of x. So this two parallel type of sign is telling you that no higher power of p would be dividing f of x. So therefore, when you focus on our formula here that we got lately, so let me rewrite this formula. A to the power k minus 1 times f of x to the power k is equal to f of x to the kth power for these values of k, right? So in view of this, so this shows that so it will work for every single k, right? So it would work for k equals 1, k equals 2, and so on. So therefore a itself has alpha p's in it, so therefore a to the power k minus 1 has alpha times k minus 1 p's in it. However, this expression here might have some additional ones as well, so therefore this is definitely less than or equal to, the inside here has beta p's in it, so beta times k for k equals 1, 2, and so on. But then here you have an infinite system of inequalities. Namely, if you plug in 1, we would get that 0 is less than or equal to beta, then alpha is less than or equal to 2 beta, 2 alpha is less than or equal to 3 beta, and so on. But then if you think about the values of alpha, so for instance, we would see that alpha is, there's nothing about alpha here, but here, well, obviously alpha is the same thing. Alpha is less than or equal to 2 beta. But then as we go further, we just realize that the upper bound for the values of alpha is constantly decreasing. In fact, in general term, it would be alpha would be less than n plus 1 over n beta. And as n goes to infinity, this would imply that alpha is basically less than or equal to beta. But then our prime p was arbitrary. We just took an arbitrary prime p, so therefore this would imply that f of x for all its primes is divisible by a. So therefore f of x, any prime that a has, f of x has more the same primes and more abundantly, in a sense. So therefore so this implies that a divides f of x as we wanted to prove. In addition, so we also realize here that not only p, our choice p is arbitrary, but the choice of x was also arbitrary. We fixed an x to begin with, so therefore it implies that for all values of f we have that these are multiples of a, or you can say that this is true for all values of x, and so therefore we get the following formula. That this would imply that if you call the quotient as this, right, for all x in positive integers, this formula clearly defines a function g from the set of positive integers to the set of positive integers such that g of 1 is equal to 1, and because f of 1 was a, so g of 1 is equal to f of 1 over a, which is a over a, which is just 1. Also, if you look into this expression that we got earlier, namely this expression here, this would imply that if I replace the f expression with the g counterpart, so that would be this would imply that a times a f of xy, g of xy is simply equal to the same thing here. We can replace the f's with a g of x times a g of y. The a's would cancel out, and as a result we would get this very, very nice result, such that g of xy is equal to g of x times g of y for all x, y in N. Now recall from our very first result, I believe this one, that f of so we have this expression. Now I can replace the f functions here with the corresponding g functions in this formula. So that would be simply f of s. So it would be let's write it down here, I guess. So we start with f of s equal to I believe it was a square s, and replacing the function f with its counterpart in g, that would simply be equal to equivalent to a g of, and then a g of s, and that's equal to, this was a square s, yeah, so this is just a square s. So therefore the a's will cancel out, so we would have g of a g of s is equal to a times s. Now if we plug in s is equal to 1 into this expression, we would get g of a times g of 1 is equal to a, but then g of 1 was defined to be 1, so this implies that g of a is in fact equal to a. So therefore a is a fixed point, namely f of 1, whatever value it is, would give you a fixed result for our function. So therefore, if we start with this expression again, we would get a times s is equal to g of a times g of s. But now we can use the multiplicative property, so we would get g of a times g of s, and that's simply equal to g of a, we just figured it is a, times g of s. And finally this would imply, after cancelling out the a's, we would get g of s is equal to s for s in positive integers. Therefore, to summarize, the two main characteristics of the function g is that g is a multiplicative function, in the sense that g of xy is equal to g of x times g of y, and secondly, we just observed that g of s is simply equal to s for any s in N. Now we need to now look into the converse statement. So conversely, let's say, we need to check if g, our function g defined on positive integers, which satisfy these two conditions with I and 2i, if it satisfies these two conditions, and if f of a is equal to a, so a is an integer, is a positive integer, I should say, such that this holds, such that this thing holds, then and if conversely, if this is true and if this is the case, then it must be that from the definition of our function g, so we can say that f of x, if we define f of x to be a times g of x, g being satisfying these two conditions, then we claim that this function satisfies, sorry for that, it satisfies the original functional equation, namely this weird condition that f of this thing, basically the functional equation. Let me just write down as the functional equation, the functional equation of the problem statement of the problem statement. Okay, so I leave it to you to check that. So proof homework, because it's already getting very long anyways. But then we still need to show that for every prime p, p prime implies that g of p is also a prime. So this is our claim actually. This turns out to be the critical claim to solving the problem. So I claim that if p is a prime, then g of p has to be a prime as well. So first of all, this condition, the second condition, immediately implies that g is a one-to-one onto function. It's a bijection actually, and as a result, g of p is not equal to g of 1, right, which is simply equal to 1. So g of p is definitely not equal to 1. But also, let's assume to the contrary, to the contrary, and by way of contradiction, let's assume that g of p is not a prime, but it's rather a product of two natural numbers and positive integers. Then by the given two characteristics of the function g, we would get that g of u times g of v is simply equal to g of, because our function g is multiplicative, uv, but then this product is just g of p, g of p, but then this is simply equal to p, which is a prime. So this implies that when you look at these two numbers, either because you have a prime here, so either g of u is equal to 1 or g of v is equal to 1. Well, if the first case holds, then this we know that if the first case holds, then yeah, because of the second property, right, because of the second property here, we can replace we can okay, so let's think of it like this. Okay, so let's start with the second property. By the second property, I know that u is equal to g of u, right? That one's for sure. And well, because if g of u is equal to 1, that means that g of u, and replace it with a 1. But then g of 1, we know from earlier that this is equal to 1. But that's a contradiction, because if u is equal to 1, that's not gonna fly, because then g of p is indeed a prime, using this relation. The same thing here will hold. G of v would simply be equal to g of 1, because that's equal to 1, and that's equal to 1. Again, the same contradiction happens. So therefore, we have found that g of p, when p is prime, g of p is also a prime. So therefore, the function g maps, so it will map the primes onto the primes, right? And therefore, if we look into so using the fact that g is a multiplicative function, let's start with g of, now let's conclude the problem. G of 1998. That thing is simply g of 1998. Prime factorization would look like, I think 37 here. And that means that because our function g is multiplicative, g of 2 times g of 3 cubed, but then we can take out the cube because again it is multiplicative. Sorry for that. Restart now, pick a time, snooze. Okay, snooze. Cubed, and then g of 37. Now these are just three numbers, so let's call g of 2 as q. This guy is an r, this one is an s. So therefore this would simply give you q times r cubed times s. And these yeah, because the function g we established earlier was an injection, it was a one-to-one function, so this implies that q r s distinct primes, q r s are distinct primes, and so so therefore this expression is definitely greater than or equal to, so if you optimize it, we can put the smallest positive integers prime that we can replace pq and qr and s, such that such that we get the lowest bound would be, I need to put the lowest prime here, and then the other two would be the other primes. So therefore I get 3 times 2 cubed times 5, so that's simply equal to 4120. So g of 1998 would simply be greater than or equal to 120 for sure. So it can't be this number, so this implies that g of 1998 is greater than or equal to 120, so it can't be less than 120. And because therefore f of 1998, which is simply equal to a times g of 1998, is simply as well greater than 120 times a, and knowing that a is the value of f of 1, but then f of the function f takes positive integer values, so the least that a can take is probably 1, so therefore this is definitely greater than or equal to 120. But is 120 attainable? So can this ever happen? So let's try to see if that might work actually. Now in fact the problem reduces to defining this function properly for at least these values, g of 2, g of 3, and g of 37, so I should be very careful on that. And a, we will simply plug it, so just take a equals 1, so therefore our function f f of x, if you take a equals 1, you would get f of x is equal to g of x. As such, it would imply f of 1998 would simply be equal to g of 1998. Let's define g carefully so that we can hit 120. So the way I will define it is the following: g of 1 I will set it equal to 1, g of 2 will be set equal to 3, g of 3 will be set equal to 2, finally g of 5 I'll set it equal to 37, and g of 37 will be set equal to 5. Once you do this, so you see the swapping business here and here, for the rest of the primes we will let g of p be equal to p for all other primes, and so when I say all other primes, I mean the primes, all the other primes except 2, 3, 5, and 37. And now if we also define g of x to be okay, so let's write it like this. So if x is simply equal to p1 alpha 1 pn alpha n, then g of x will be defined as g of p1 alpha 1 up to g of pn alpha n, and as a result, if that's the case, then the two properties that define g are satisfied. So we have a well-defined function here, and as a result, using this definition now, for instance, let's test it. G of 1998, which is simply g of 2, g of 2, 3 cubed and 37, 2 g of 3 cubed, and g of 37 would simply be equal to g of 2. We defined it as 3 times g of 3 cubed is just 2 cubed times, and g of 37 we defined it as just 5. And sure enough, this way we are able to attain the value of 120. And because f of 1998, when we pick a is equal to 1, is simply equal to g of 1998, we get again a 120, and that solves our problem. Hope to see you guys in our next video.